So again, I'm Adam Temple, CEO of Evolved Extraction. Um, we help extractors accelerate profitability, and a few ways that we do that we'll discuss on the call here, primarily through our genome technology platform, which includes a lot of modular upgrades. And particularly the genome crystallizer is kind of a core product for us that we can integrate crystallization functionality into any hydrocarbon system. We're not going to be talking as much about that today. We're going to be talking and focusing more on how to accelerate your profitability through increased efficiency and increased throughput in your hydrocarbon extraction system. But we help extractors in a lot of different ways, increase their efficiency and their productivity, and a lot of that is through our consulting services. So we offer our equipment along with consulting and engineering services to integrate with existing systems. So we can solve pretty much any problem and alleviate any bottleneck in your extraction process with that combination of service and equipment. And and then really that's done through our chief technology uh, officer, Lyndon. And one of the most brilliant guys, I think, in the development of extraction technology, the inventor of the genome crystallizer, and kind of bringing inline crystallization processes into the mainstream production methodologies for hydrocarbon extraction. And so Lyndon leads our team of engineers and helps people kind of implement these techniques and these technologies through our services and through our technology platform. We also have Murphy Murray who's going to be joining. I think she's having a little bit of technical difficulties, but we will start without her and we'll get her to kind of reintroduce herself when she joins. And over to you, Lyndon. Anything you want to say to kind of introduce the topic and what you've been up to?
Yeah, thanks for the kind words in the intro. No, we're just going to be running through some some common bottlenecks that we see time and time again in hydrocarbon extraction in particular, and talk about some of the ways that we can pretty significantly impact your throughput, your production throughput relatively easily. And a lot of these will be takeaways that you can kind of do on your own as well. What's interesting about this industry is there's a lot of low-hanging fruit. There's a lot of really easy, impactful things that can be done to increase how much biomass you can get through in a day and how much isolate or whatever you're producing you can put out in a month kind of thing. So there's Murphy. Murphy, do you want to give a brief intro?
Sure, yeah. Hi, everybody. Murphy Murray. I have been working in this industry for decades now. That being plural is crazy. But, I keep getting older and the extraction problems seem to kind of stay the same. We just, all our problems scale. So I've been working on the operator side. I own and operate licensed businesses. I've also worked with manufacturers at varying levels, and my, primary focus as a consultant is training and developing products, developing processes to make those products, and developing staff. So as a consultant, I really focus on, optimization and having a grounded approach to analyzing your processes, which I think is uniquely applicable to the extraction industry in a way that it's applicable everywhere, but we get fast results in extraction. We can find a problem, root it out, and remove it with a speed that you don't get in retail, that you don't get in cultivation, that you don't get in anything except maybe finance. Like we actually get to operate in some pretty nice pockets of math and numbers and predictability. And so that pattern recognition is something I've spent a lot of time on. And like I said, I've been doing it for a long time. With each problem we solve, we introduce a new one. So I don't think I'll be out of a job in that sense very soon. But I do enjoy going out and solving those problems for everyone. And when they call me 2 years later to say we've tripled throughput and now it's a new problem, I can't wait.
Yeah, there's always going to be a bottleneck, right? So, so just to do some kind of housekeeping stuff. So just a brief introduction of what Genome is. So the mashing of Evolved and Yellowstone. We teamed up a few years ago to bring our hydrocarbon systems. We were both very focused on ethanol at the time, and brought our crystallization line to market. Um, we do, we are an OEM, so we do a lot of, we manufacture components, and then we kind of assemble them into modules to solve these specific problems, and then we do kind of full lab build outs or sequences for folks. And we do a lot of our business is actually integration. So people have existing systems, and we take these individual components and we kind of build out their labs to increase the throughput and increase their capabilities. This was a really interesting poll that Murphy did a while back that essentially, yeah, 80%, in short, 80% of all hydrocarbon closed loop extractors are altered after their purchase. And so that's really the space that we, we acknowledge and we thrive in, is that everybody's modifying their machines and tweaking them to suit their needs a little bit better. And so we come in and facilitate that essentially with our engineering services, and in many cases with Murphy's training. Yeah, so we've got we're up in Canada for our R&D portion of what we do, and we have a demo facility that's licensed by Health Canada for research. And so we do really quick prototyping. It's actually connected to our fab shop, and so we get to live out our operator. When we were operators, we always had this dream of solving our frustrations in that we have a TIG welding setup, and we can bring components in really quick and develop them as we see fit, as opposed to waiting. But yeah, we host a lot of, we do seminars with Murphy, we do feasibility testing and product demos, and we're always kind of doing experiments inside the lab. It's a lot of fun. This is us. Introduced us. Super quick, the kind of itinerary, what we're going to go through is we've covered introductions, but we'll talk about some low-hanging fruit. Like I was saying, this industry is very interesting in that there's almost always some low-hanging fruit in these labs that we go into, whether it's a couple of heat exchangers or some valves that can make an enormous impact. That is rare, when you compare it to brewing and food processing and stuff like that, much more streamlined industries. And then we'll go through 5 bottlenecks. We've got stuff about columns, we've got stuff about solvent recovery, we've got stuff about just the general flow of the systems, and then we'll talk about some energy stuff. And then as a bonus minute, we'll talk about the regenerator, which is a very interesting heat exchanger concept. One thing we found last webinar was that we went through this material relatively quick. I think it took us, half an hour, and then we got an enormous amount of questions, and we were able to address them individually, and that fostered a lot of good dialogue. And so if you have questions as we go, just pop them into the questions icon at the or the question box at the top, and then we'll kind of go through them. We'll try and address them all. The other thing is that we're using some tags to see what people are interested in. And so we've got another webinar that's coming up that is all around making, these minute changes to your process to shave, pretty much the idea is to shave a few minutes off of every column. And that has a tremendous impact over the large scale when you look at it over a year. So just comment minutes if you guys want to be tagged, if you guys want us to follow up with that. And then if you want to know more about crystallization, that's something we're doing another webinar in. Just type in crystallization in the question set, and we can make sure that we reach out to you and answer those questions. So let's dive into it. We'll just dive into our first area of discussion. Margie, do you have any other prelude you want to do?
No, other than just to echo that the questions I think really make these webinars. We know what we want you guys to know. We don't know what you already know or what you want to know. So, share your questions, even if you think it might be about to be answered or that it's a silly question. We're here to answer them. So please speak up.
Throw us a curveball if you can. Yeah, well, it'll be fun to answer. So yeah, let's start with some low-hanging fruit. What is kind of the first impactful way that we see that almost every lab can improve? A lot of the early systems that were out there were assembled in a way with, they've got quick connects and they've got loose lines, and or people that built their own systems, especially, out of West Valley back parts and stuff like that. They have multiple lines that they disconnect and reconnect, and it gives them versatility. You can switch different things around, but and achieve different goals. But once you get into a production setup, having hoses that you disconnect and reconnect actually has a huge impact to the net output of your system. And so we find this in almost every single lab, and it's something that after this webinar you can go back in your lab and you can fix. Is if you add enough valves and hoses such that everything is manifolded so that you are never disconnecting things before you move, as you move through the steps, you can save a lot of time. We find that if you can save, this math as I find illustrates it very well, is that if you can save 1 minute per column, you can sometimes in many situations, if you have the solvent recovery to support it and whatnot, you can run an extra 4 to 5 columns in a day if you're running 10-minute columns. And the impact of that is hundreds of thousands of dollars of output production in some cases. So it's, when you look at the price of valves and hoses and stuff like that, we're a really strong proponent of manifolding things out. And actually, something that Murphy came up with and we implemented was also not just the decrease of the jangling, but also this color coding. You want to talk about the color coding a bit? Or?
Yeah, so this is something I learned as a result of teaching. And, like the first extraction tech system where I was training operators on back in like 2014, most of the time in that training session is spent answering the question, is this the solvent line? Is this one the oil? Where does this one go? And for some people, they are process flow diagram people. They can look at the way it's supposed to be mapped out and they can follow it. And for a lot of people, it's just spaghetti until they get used to it. And where that trips operators up the most, I think, is their second job, not the first one. Because the first one, they're willing to sit and train you and say, here's how this system works. And everyone would like to think they've got a very proprietary piece of information with that. But what I've found is that once you can follow a process flow diagram, you can kind of run any extractor. It's much like driving a car. If you know how to drive stick and you know how to drive an automatic transmission, then it doesn't matter if you've only driven Jeeps. You can get into a Subaru. And the same is true for a lot of these extraction systems. They may have valves that look different. They may have a valve in a different location. But if you can follow the flow, you can figure out what's happening and what you're supposed to do next and respond to an emergency much more easily without as much just physical repetition of knowing that every time it's this valve that I open and close. And color coding makes it much easier to see that when you're looking at a sea of stainless. So the color coding in these cases is a combination of following the process line, but also insulating it. Because another issue that comes up, for example, is I used to use red and blue hoses for my heaters back in those 2014 days. And that was really cool because I knew which one was going to the system hottest and which one was going away from the system colder, but I wasn't insulating it. So they were both inefficient. And once I wrapped that black pipe insulation around it, now my color coding went out the door. And so this combines both things, insulating those lines so that what I think is happening is actually happening, and then also being able to quickly and easily identify where something goes, where it's coming from, so that in an emergency, I can say to a person who doesn't normally run the extractor, go close all the valves on the red lines. And in a non-emergency, I can train someone and say, now, when you're filling this column, you should only have valves open on this blue line. And now I can communicate things without, I've seen a lot of numbering systems for valves, a lot of, very engineer, a piece of paper oriented processes, but color coding almost always works. If you are colorblind, thank you for nagging me so hard. They're the only people this doesn't apply to. But for the rest of us, the color coding makes it very easy. It's much like electrical work, right? Electrical wires didn't used to be color coded. And that was a hard job for electricians. And now most people can put a new cord on, a power tool. Most most simple electronics are accessible and easy for people to figure out, which I think is extremely important for these operators. The easier it is for them to get comfortable with the system and confident with the system, the faster they'll be. If you're slow at attaching hoses, I kind of want you to be, because the fast version isn't necessarily safer. And what'll make someone faster is being able at a glance to know exactly what comes next. All of the handles on your valves can be color coded. There's a lot of color coding in the fittings that you can request. Of course, fees for everything. Swedgelock would love to give you a yellow quick connect instead, with a little upgrade. But that at a glance recognition of where things are in the system, you will train people faster, and they will be competent and expert level operators faster when they can very easily see that entire process flow without having to think too much or learn a new custom set of intellectual vocabulary.
Yeah, absolutely. And as we see people, we see it a lot. They're bringing in new people into the industry a lot now, right? It's not expert extractors they're coming in. So we definitely, yeah, preach that clear communication definitely starts with this.
Elena, can you explain a little bit like what distinguishes our approach to like the jangling approach and why it can shave off, a minute or a few minutes per column?
Yeah, so really it's all the cumulative steps that you take when you are disconnecting a hose, reconnecting it, potentially dealing with a clogged quick connect, and maybe you have a leak, maybe you have resin that spills out, and now you can't retighten your JIC fitting or whatever because it's completely filled with crude. All of those steps are very cumulative, and so if you instead have the decision to run a column or the decision to add a little bit more solvent and then push with some nitrogen and then vacuum it up to make sure it's full. All of these individual steps can be done a lot faster, and so you can shave an enormous amount of time by having everything in one manifold in one area.
So it's just an exercise of kind of redesigning the process flow with a lot more manifolding and kind of thoughtful approach to the design of the fluid flow.
Yeah, and I think that folks were rightfully, resistant to this, and initially because you're like, well, we might still keep changing this, and we were the worst for this. We changed our lab every single day for 5 years. But once you get your process locked in, spending the extra time and money on a nice manifolding system so that everything is accessible and within a moment's reach is very effective and very easy to do.
We're eliminating process steps in terms of, like, if I don't have to take a hose off and I don't have to put it on again, that's a minute and a half if you're a NASCAR pit crew, that I've saved, but also physical steps, right? So if you have to take the lid off of your column and then turn around and walk 2 steps to set it down before you turn around and walk 2 steps back up a step ladder, if you're me, and then grab the, material to pull it out, literal physical steps will eat you up in the lab because they add more time. So let's say it's a minute and a half to reattach those hoses. It's also probably a minute of physically moving. And then later on, you're going to have more minutes in cleaning up the space where the physical movement was happening. The further that you have to physically walk to do each step of this process, the more likely things can go wrong, the longer it's going to take, obviously, the harder it's going to be to train other people, and it will physically take up more space in your booth. Booth space is a hot commodity. Lyndon doesn't know this because he has the biggest booth you've ever been in. But for the rest of us, like for most people, to go up on the step ladder means hitting their head on the light fixture. And so anytime that you can stop that physical movement, those pivots, you are going to have a cleaner lab, and it's going to be a much tighter process. It's hard to go fast when you have to physically move. I bring up NASCAR pit crews a lot when I'm training people, and the key there is, like, each guy has one tire, and he shows up to that tire with every tool he needs. And if he had to run back to the pit to do something to tighten that tire, there's no way you win the race. And so those physical footsteps are also eliminated when you aren't having to take things apart. If you need more than the wrench in your hand, to do a column swap. If that's a 2-tool process or a 3-tool process, because you have different size fittings on all of these components, it will eat you up in time and efficiency. I can't tell you how often I hear the phrase, where's the flashlight? Where's the wrench? My goodness, if you don't have to leave the spot where you use the wrench, you won't lose the wrench.
I think, Glenn, we got a little kind of a little feature for that as well, right? Like a little wrench holding mechanism and
Oh
a
yeah, we
tray
got
as
some
well that fixes.
accessories. Yeah, definitely some tool trays right up next to your columns and whatnot, so that you're not dropping things. And to Murray's point, so you're not turning around and catching valves with your lab coat and stuff like that. There's a bunch of stuff there for sure. Um,
Another little thing to mention is that that giant booth that Murphy was talking about, that's our Genome Technology Center. We're actually running client demos there today while Lyndon's kind of in here on the intrawebs with us. But feel free if to type in demo at any point during the webinar. If you're curious about something and you want kind of a live demo in the booth, visitors are always welcome, and we love to host guests. So yeah, feel free to drop that as well.
okay, I'm gonna move us along just to some of the bottlenecks here now. Um, So we were talking a lot about, tooling and stuff like that for column switchover, but just column switchover in general, we still come into a lot of facilities where this is their bottleneck, and it's one of the easier ones to overcome as well. Is just we often measure the net throughput of somebody's facility and how fast they can switch columns over. And sometimes that's limited by solvent recovery, which we'll cover, but a lot of the times they just don't have enough material columns, and so you are yeah, the question you have to ask yourself is how long does it take to change your column over before you can start the next extraction? And do you need more columns? It's often the first thing that if you can be low, the general idea that we operate around is that you always want to be extracting. If you can be extracting 100% of the time, that's as fast as you can go on that process. And so as long as you can be filling a column, while another one's being unloaded, while another one's running, we typically see 3 as kind of the minimum, where you can kind of be doing all of these steps at once. Because there's kind of this pitfall where people fall into where like, oh, I have, 8 columns or I have 10 columns, and they load them all in advance. But then you still have to reload all of those columns by the time they're all done. So it is good to have not too many columns, but the right amount so that you can be continuously extracting and replacing and swapping stuff out as you go. That's a relatively easy one. Or if you have anything on that, just add more columns if you need them, kind of thing.
I would just add that if you don't know exactly how long it takes for you to do a column switchover right now, get yourself a stopwatch. Don't time yourself. Have someone else time you, and have that other person write down everything that you do. Because a lot of times we are sort of blind to what makes us slow in those moments. So, for example, a lot of people forget the walking around part of their process. They forget the walking the extracted material out to the dumpster when they're calculating all of the minutes that their staff is using per day. And it's easy to look at like this is a common error that happens on both sides in the equipment sales game, is that the equipment manufacturer is going to give you the optimum speed. If all of these columns are full and extracted, this is how much you could potentially produce per day. And that equipment manufacturer isn't considering the fact that you modified the way that it's installed in the booth, and your staff can't get behind it to make it easy to take the lids off. So they have to do a weird thing and a hard thing. They're not calculating all those little extras that your own infrastructure might impose on you. And they're not calculating for, the sort of habits that people will get into, which is especially common when you are increasing a smaller system to a larger one. You are going to have to kind of break the habits that people get used to. So, for example, someone might have 4 columns on the front of their system, and what they'll do is load all 4 and then run one, and then run one, and then run one, because they're used to loading one and running one, and they forget that I can keep going while the first one's going. They start with a batch system, and they don't train their brain and their mind to start operating differently. And one of the easiest ways for you to get some visibility on that is to actually time yourself. Start measuring these numbers and go into it with curiosity. There's not a good number or a bad number. There's your number, and then there's room for improvement, whatever that is.
Yeah, we
Yeah.
often come in and folks are running at about, an hour to a half an hour per column. Some people are down to 15, and really we're always trying to get people down to the 7 or 8 minute per column mark.
Yeah, if you're not
And I
under
think
15, there's so much we can do.
the other thing to make sure, like you keep in mind, is that we're measuring a per column switchover time because we're running a continuous extraction. We're never waiting for solvent to recover before we start the next cycle. So you're just doing column, 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 and the solvent is evaporating and recondensing at the same rate that it's being used in the extraction process. That's not true for a lot of systems. So if your system requires you to recover the solvent before you start the next set of columns, you really have to measure the entire cycle time and then divide it by the number of columns.
Yeah. Yeah, exactly. Getting set up for half the day, running all your columns in a couple hours doesn't count. You really need to average over the day for sure. We'll talk about that in start-stop systems. We have a slide on that. One thing, the next kind of bottleneck that we see a lot of is active recovery. So active recovery is when you use a compression pump to recover your solvent, and it is limited by a number of things. One is that you have a fixed displacement inside of these pumps, and so you can only draw in as much gas as it can hold. And so the only way to increase your process speed is to buy more of these pumps. The other thing is that these pumps actually add an enormous amount of heat to your process. You're compressing a gas, and that puts a lot of energy into the system. And you then have to reject that heat. You have to cool your solvent back down before you can do your next extraction. And so one of the first upgrades we often do for folks is we get some plate exchange, some heat exchangers involved, and we go over to passive recovery. So active recovery is slow and inefficient because you're adding heat to the system, and you have a fixed amount of gas that you can pump. And we often see, somewhere around a pound per minute with a lot of the typical GC 5000s and Corkins and stuff that are out there. You can get them a little bit faster if you can get your inlet pressure a little bit higher and whatnot, but it's relatively slow. Whereas when you go to passive recovery, which is condensing on a cold surface, so you have your hot collection pot and then you've got a cold plate exchanger, you're only limited by the capacity of your chiller and the surface area of these heat exchangers, which are very inexpensive compared to a pump. And so you can really get enormous recovery rates. And to Adam's point, what he was saying before, you can get to these recovery rates where solvent recovery is no longer a consideration. Really, from my perspective, your goal should always be to have column changeovers be your bottleneck, because that is a human. There's just only so fast you can open and close a 6-inch or an 8-inch dry clamp, and it still be reasonable, and that. So it's kind of a natural max rate. Yeah, anything on passive recovery? Oh, the other thing that's really nice about passive recovery is recovery pumps are dangerous. They can generate 400 psi at their outlet really easily. It's enough to do some significant damage. With passive recovery systems, the whole all of your pressure that gets created gets condensed, and so you don't have anything that can create any pressure really. You can, obviously you can shut the valve on your recovery pot and that'll climb up to 60 psi or something like that. But for the most part, passive recovery systems operate at 5 or 10, and that's pretty safe. That's a lot less than a bike tire. It's relatively relaxed.
Yeah, the safety can't be overstated, I think, because the way that a passive system functions requires an appropriate pressure differential. So the greater the difference between, your evaporation pressure and the pressure in the vessel where you're recovering to, the faster you can go. And so along those lines, your control over your temperatures and your pressure is your recovery speed. And what's great about that from a safety perspective is that if you fail to generate enough pressure or you have too much back pressure in that receiving vessel, what will happen is nothing. Passive recovery will just stop. It will just equalize. Whereas with a pump, it will work better like the best performance you can get out of a recovery pump requires the minimum conditions required for passive recovery. So if you can run a pump and it's happy, you can run passive. But because a pump can pull and push in a way that passive sort of just allows a siphoning effect to occur, that pull and push can allow you to waste your own time in significant ways. And so, a lot of times, what I see with people's recovery pumps is that they can't generate enough heat in order to build that pressure up. So, that recovery pump is actually pulling against like a vacuum in that recovery vessel. And this is a problem for several reasons. The first being that there is almost no gas inside of that pump. Every time that it's pulling, you are getting just milligrams of amounts. And so you might hear that fast, compressor, and it'll sound very busy, but it's getting nowhere. That's like a burnout with your tires. It sounds impressive, it's doing nothing. So that's slow recovery with a massive amount of energy. But it also allows you, because you're pulling vacuum, to suck things out of that collection vessel that shouldn't come out. So you can aspirate, you can have misting, you can get stuff that isn't just your solvent because you're not distilling if you don't have any positive pressure. And it creates an opportunity for you to break that pump because those pumps do not like to pull vacuum. And when you run them at vacuum for a very long time, you can dry them out. So that's where like the MVPs people are cracking those diaphragm seals. If you're rebuilding your recovery pump more than once a year, you better be processing millions of pounds. And even then, if you switch to passive, there's nothing to rebuild. You might
And nothing
replace
to
the
break
hoses on a
either. Yeah.
manufacturer recommendation. But yeah, the worst case scenario with passive is nothing happened. Whereas with a pump, you can run that pump until it breaks itself, or you can run that pump in a way that you break it. And it's very common. And I know a lot of people were running the pneumatic pumps for a while, and that was exactly the issue they ran into, is a lot of constant rebuilds because they were pulling under vacuum. So if you don't see positive pressure on that collection vessel at all times, first of all, you have other problems we'd love to help you solve. But second of all, you're killing your pump. Your pump hates you if that collection vessel is at zero and if you're pulling down to a vacuum. So it's just not suited for what most people are applying it towards.
Yeah, and I think the rebuilds is definitely a problem, but like the bigger problem also is like the reliability. If you're relying on something that you might have to rebuild, and then your production goes down, I think one of the things that we often get our clients to calculate is what is your cost of downtime? What is the gross profit that you would produce in a day if you're operating and you still have all those same fixed costs as if you were operating, but you're not producing any revenue that day, and that has a cost, right? And it's a lot more expensive to go down for a week than it is to even make an upgrade to a passive system in a lot of cases.
You can always do both. If you want, if you're scared to let go of that recovery pump, it's very easy to build a manifold that allows you to run passively until you run out of enough heat or your tank is too hot because you don't have enough chilling and you need to push into it. If you wanted to take advantage of warm gas, which I think we're going to get into regenerators later, and I prefer that, but you can take advantage of the heat with a pump. There are ways to use a compressor with gas that are still going to be efficient. You don't have to give it all the way up. I think you're going to want that floor space once you switch to passive if you haven't already. But you can always build a manifold so that you're not married, so that you can go to the pump or not. It's just it's an important one to consider because if you can't run passive thermodynamically, you are not maximizing the pump. So to spend 20,000 or more on a recovery pump that isn't faster than a process without any moving parts, a little silly.
One of the problems I think that leads people to not want to go to passive recovery is this issue that it's difficult to recover solvent at the same time as you're doing extraction. So with a recovery pump, even if your collection pot is at a lower pressure than your solvent tank, you can still send your solvent through it and you can still recover at the same time. And so we view this, well, we see that as a really common bottleneck is that people are stopping and starting their systems um, such that, you're extracting for a little bit and then you're waiting for recovery. And then doing extraction and you're waiting for recovery. And that is a big hurdle. That's a big hump that if you can get over so that you are extracting 100% of the time, you can extract typically twice as fast. And so again, it comes back to that, that column time evaluation where you're saying, well, we can run a column in 10 minutes, but that's only after you spend, but after that, you have to, recover for half an hour. That doesn't really count. It really has to be averaged. And so when we talk about start-stop systems, we much prefer a continuous system. And the way that we do that is we pump our solvent as a liquid. So we were just hating on gas pumps a little bit, but I feel very differently about liquid pumps in the sense that a liquid pump at every articulation can pump a couple pounds of liquid solvent. You can pump easily 500 pounds an hour or 1,000 pounds an hour. And what we're doing here is we are pumping the liquid solvent through our biomass columns, and we are passively recovering at the same time. What's happening here is that as we drain this tank out, you're lowering the pressure in your solvent tank and maintaining a lower pressure in your solvent tank. And you're pumping it through your column and into your collection pot where it hits the hot surface, increases the pressure, and wants to go back to the low pressure zone. And you get a system that goes kind of faster and faster as it runs, because now as you're condensing passively, you're cooling your solvent tank down, you're cooling your lines down, and you have a continuous system that never has any breaks. And so, yeah, we're a strong proponent of continuous systems versus, stopping and starting, extracting, then recovering.
One huge benefit of that liquid pump too is that if you're currently using nitrogen to pressurize your tank in order to transfer solvent from the tank to your columns, that nitrogen is room temperature at best. So you are also adding heat to that tank every time you pressurize with nitrogen. And even though it's not as hot as the heat coming out of a compressor, it still is interfering with that temperature control. And so if you are trying really hard to keep your gas cold, but you're heating it up every time you need to drain it, you are just kind of working against yourself. And so that's a loss of energy and a consumable product. Every time you are pressurizing and then depressurizing a tank, you're changing that temperature and just throwing away vapor. If there's a place you want to pump, it's probably to compress and reuse that nitrogen.
Yeah, that's how we use recovery pumps actually, is after every column is done, we chase it with nitrogen, we pump the nitrogen. That's fair. But you just don't want to be reliant on it for the entirety of your mass flow of your solvent. That's the other thing too, is that's a significant, pretty significant hazard that we see is like pushing with nitrogen. First of all, it stops your recovery. You can't be recovering while you're pushing with nitrogen, but also off-gassing that nitrogen when you're done to lower your pressure again and start recovery is you're taking a lot of propane, especially goes with your nitrogen and off-gasses into the booth, and it's unsustainable in the long term. I don't think that'll.
And it's a physical task. Now that operator has to be manually opening a valve somewhere, usually walking over to the recovery tank to do that and walking away from the process that, they should be managing. And so, it kind of goes back to like the job you should be doing should be filling a jar or loading and unloading a column.
Right.
Needing to touch other stuff is like, imagine if you had to, you know, facilitate the flow of fuel before you press the gas in your car. Like, no, we want one or two actions, for each operator where they're standing. And so anything that requires you to literally walk from one end of this process to the other, like having to add the nitrogen and then vent it again, huge opportunity for risk. And that nitrogen comes to you in bottles that are much higher pressure. And so even though it's not flammable or combustible, you are still creating an opportunity where you can overpressurize components of your system, which, going back to pumps, those, butane and propane compressors and recovery pumps, they are not designed for dry nitrogen, and they can't condense dry nitrogen into a liquid, which is what they want to do. So all they do is get hot and break. And so, nitrogen is a great tool, but it shouldn't be a crutch that you use instead of a leg. You want to support your process with it and not use it to replace a recovery pump. It's not sort of nitrogen or pump, it's thermodynamic control and pressure differential supported by those other two items wherever it can be.
Yeah, definitely understanding the vapor pressure in your system is the most core concept for sure. Just the simple fact that, yeah, hot gas wants to be cold. It wants to go to a lower pressure, lower energy state. And so if you have a high pressure area somewhere and a low pressure somewhere, it will go as fast as it can travel through the pipe to get there. The next bottleneck that we see a ton of is improper heater and chiller sizing. Almost everywhere we go, there is ineffective, like undersized heating or undersized cooling. And so when we look at, why that's important and where that is, so just to cover it, so you have heat going into your collection pot. You're typically sending 40 degrees Celsius. Sorry, I don't know that in Fahrenheit. You're sending hot water into your collection pot jacket, and you're boiling the butane, and then you're rejecting that heat through a chiller. Whether you're using a compressor pump or not, you're always using a chiller, and you're rejecting that heat out. And so what we're talking about here is not the temperature that you're doing these processes at per se. We're really looking at the amount of kilowatts that are transferred through this process, which is a very important distinction, because a lot of people tell us, my chiller's sweet, it goes to -80. But that unfortunately doesn't translate to the amount of kilowatts that is actually rejected. The amount of energy that is moving through the system is directly proportionate to the amount of solvent that's going to boil off. I've got some graphs here solvent recovery is on the left side. So it's the amount of solvent in pounds per minute you're recovering based on your heat that you put in and your chilling that go out. You have to have both of those. So, at around 10 kilowatts, you're 3.5 pounds per minute. 15 kilowatts, you're 5 pounds a minute, and it's proportionally directly correlated. If you get a bigger chiller that has twice the capacity, you will go twice as fast, provided you have the heat exchanger surface area to match
And
it.
you have to have
And
a
so,
balance, right? You have to have the heat and the cool balance. So if you just get a giant chiller and you don't supplement with the required heat to match the same amount of kilowatts, you're not going to maximize the throughput of that.
yeah, you'll freeze your hot water, and that's no good. It has to be 1-to-1, really. And then, if we look at, the biomass that you can extract versus the energy in and out, it's proportionate as well. It scales exactly the same. You can extract twice as much with twice the energy capacity. And then same thing with THCA, right? Because that's just a proportion of the biomass. So everything, that's probably one of the most impactful, one of the many impactful things you can do as well is increasing the capacity of your chillers. And just to kind of touch on to get an understanding of kilowatts is, I thought that this was a good illustration because people have interact with these a lot, but this is kind of what 3 kilowatts it looks like. So when you look at these individual heating supplies, heat's relatively cheap, right? But a lot of the early systems came with these labware stuff. So this temperature controller, this little Hubert, is a fantastic piece of equipment for very precisely controlling the temperature of lab equipment. But when you're talking about an industrial process, it's only 2 kilowatts, right? It's like putting something on your stove. It's too small. But if you get into these on-demand hot water heaters that are used for heating an entire building through in-floor heating, you're getting into 54 kilowatts. It's infinite. You're probably not going to buy a chiller that can reject 54 kilowatts. And so you can kind of one and done all of your hot water supply with something that's relatively inexpensive and very serviceable by local plumbers, right? These guys come, they install, they hook it up to propane or natural gas, and you never have to think about heat again. And then this kind of gets into the kind of the chiller capacity. So if you, we see people, I've been to a lot of labs, this has slowed down obviously, but they were using chest freezers to cool down their solvent. We used to do this, we used to do this as well too if we're doing something overnight, but it's literally a fraction of a kilowatt. And then these, again, these Hubers, amazing pieces of equipment for, control and data collection and stuff like that, but they're not an industrial tool. You have to really look at industrial chillers to get, in the 20 kilowatt range, or now a lot of people are doing 40 and 60 kilowatt kind of ranges for these large industrial facilities. Is you have to have a tool that's designed for transferring as many kilowatts at the temperature that you need as possible. Not having to think about your heating and cooling is a luxury, but yeah, Murphy?
I would just add to, a lot of these components, we think about their cost and associate that with their performance when we're buying them. So, if you have one of those 2 kilowatt or 3 kilowatt little Huber recirculators, it's probably $7,000 to $12,000 when you bought it. And, so it hurts to find out that you can get an on-demand unit and a giant tank to support it for so much cheaper. But that cost isn't necessarily a reflection of the performance. So that big chiller that's on the screen from G&D versus the Huber in the middle, the G&D is cheaper than the Huber in the middle, fundamentally. It costs more for you to install it compared to uncrating a chiller and rolling it into the room. But if your chiller's on wheels, it's because it needs repairs. It's because it has to be moved from service often, right? Like you want to look at this equipment in sort of this more long-term and scalable perspective. The size of the reservoir on those little heaters explains why they're 2 kilowatts, because they're designed for systems where they are maybe heating 1 or 2 liters of fluid in a process somewhere. And so if the reservoir on your heater or chiller doesn't at least match the jacket volume of the vessels that you are trying to heat or chill, you are not going to get very far with that because you are going to run out of that built up, stored energy. That's why I love the G&D chillers. I've got a G&D 40 and it's a 90-gallon reservoir. So, I can completely replace all the fluid in my system and send it back. And at no point has that second compressor ever even turned on. And, what you will find when you move from the smaller heaters and chillers to the larger ones is that the fluid matters more than ever. Because when you want that optimal performance, now we're talking about using the right fluid for the chiller, something that's going to hold up over time. Because now what you don't have is an extra Huber because the one that went down got repaired and replaced. So you bought a second one. Now you just have to have planned downtime and scheduled maintenance. So, as you scale up, you have to include that maintenance program into your processing because while you can get a 60 kilowatt chiller to chill everything in your building, do you want everything in your building to be subject to risk on that maintenance day? Because it might be the same day as your giant biomass delivery. It would be pretty standard for that to be the case. So, looking at, the volume of fluid you really need to chill. That way, every time you buy a new piece of equipment, just calculate that jacket volume, calculate the distance it has to go. I can't tell you how many people build their C1D1 in the middle of the building, which makes them very poor candidates for an outdoor chiller because now we have to plumb that chiller 85 feet to get to where the C1D1 is. And so this is an infrastructure problem that you can fight for years or, very thoughtfully consider upfront because you can estimate that jacket volume. You can estimate the thermal demands of just piping that stuff as far as it needs to go. And this is some pretty standard, construction and fluid management, work that there are experts out there who can help you with. They just are rarely the people who sold you the extraction equipment. And I say rarely, I know we're all on this call together now, but a lot of times people who are distributors for Huber or Julava or, across international, they are making that product available to you. That's not necessarily an indication of it being the best available product for your facility.
Yeah, especially as you try and increase your throughputs, right? You need to get something that's going to scale with you.
And you usually want to get that first. Buy extra tanks later, buy the big chiller today.
Mhm.
Yeah, and we can help you with the sizing and any of those calculations. We support that through our engineering services, so you're not alone in making these calculations. I think another thing you mentioned there, Murphy, was cost of these chiller waters, or sorry, cost of these chillers on a per kilowatt basis. We actually have a calculator that measures the cost per kilowatt, so the upfront cost you have to
Okay.
pay relative to the number of kilowatts that you get at any given temperature, and that's an important metric to be looking at when you're making these purchasing decisions.
Yeah, for sure. Um, so the last bottleneck that we've got here is the regenerator, which is a really interesting um, heat efficiency booster. So we have this, within the cannabis extraction process, we have this really useful fact that you are cooling down all of your solvent to do your extraction. And then, you perform your extraction. That cold solvent goes into your collection vessel where you're trying to boil it off. So you've got cold solvent going into somewhere where you need to heat it up. And then as you boil it off, you boil off that, you create this vapor and you're trying to condense it. You're trying to cool it back down. And so what a regenerator is, and it's used in a whole bunch of industries, is it uses the cold from extraction to condense your gas that's coming off your collection pot. And so what we're doing here is as your cold solvent leaves your columns, it cools down a big shell and tube heat exchanger. We use a shell and tube because shell and tube heat exchangers are cleanable and we're sending resin through it. And so you need to have a cleanable heat exchanger. But yeah, so you're sending, your minus 40 Fahrenheit or Celsius solution through your shell and tube heat exchanger and cooling it down. And then on the other side, it is condensing the gas that's coming off of your collection vessel. And it has a tremendous impact. It's almost you can almost it's about 35%, I think, is kind of the maximum efficiency that you can gain, and it increases your boiling rate because you're no longer sending cold micella or cold butane into your collection pot. It's preheated, and you are pre-condensing almost a third of your gas before it even gets to your plate exchanger. And so one single heat exchanger can increase your recovery rates by about 35% without impacting the energy consumption of your heater or your chiller. So you don't, that's sometimes what happens is like, oh, like Murphy said, we're 85 feet away from the closest wall and we can't get into your chiller. Well, sometimes you can actually get a significant amount of additional throughput without actually changing your heating and chilling, or while you wait for your chiller's lead time to elapse. So very interesting process. It's very standard in a lot of solvent recovery applications, and we use it here as well.
And then Lennon, you want to just touch on also like there's another heat exchanger in here as well. That's the main condenser as well, right? I'm not
Yeah,
sure if you.
so it goes through to follow our vapor path. The vapor is created in our warm collection vessel. It boils, the butane boils off. We go send it through a molecular sieve to pull it in water. It goes through the regenerator, and that condenses about 35% of it, or cools the gas down. And then we go through a plate exchanger, a different type of heat exchanger, which has an enormous. It has 20 or 40 many parallel plates that are cooled by the chiller. And so the remaining vapor that wasn't condensed by the regenerator bounces around in that heat exchanger. The molecules dissipate their energy into those plates and it condenses your gas and goes back as a liquid. And often, if you've sized it properly, it condenses the gas and cools it. And so you're close to your extraction temperature by the time you get back to your solvent tank. And then I guess while we're at it, we should talk about the other plate exchanger that we use, which is to cool your solvent on your way to extraction. So you come, let's say you're condensing, at 0 degrees Celsius or minus 10. Then as you pump it out of the tank to send it back through the loop, you go through another plate exchanger, which cools it down to your extraction temperature, minus 40. And again, the game here is just surface area and kilowatt capacity. How much
Yeah, I think some of the other systems I've seen. they have that coil and coil heat exchanger on the way to the
The
right,
ice
which is
creator. Yeah, the ice
let's just
creator.
talk
Boo.
about well, and then the surface area, like what? Let's compare the surface area to a coil and coil heat exchanger
It's
to
like
versus
40x. Yeah, it's
something like
Yeah.
that.
tremendous. You can get a
Yeah.
lot of different sizes of plate exchangers, but like Linda mentioned earlier, that heat exchanger can be a great shortcut when you don't have the kilowatts or the, gallons per minute giant pump on a big industrial chiller. Because the amount of surface area that a plate exchanger can pack into a small container is incredible. And plate exchangers can be mounted to the walls, which I also love. And so you can take advantage of gravity, heat going up and cold coming down, and you can make an even weak chiller much more effective by taking advantage of the proper heat exchanger. Coils are super prone to clogs, and a plate exchanger is just not going to have those same issues because it's a tremendous amount of surface area, but it's a lot more free flowing inside compared to that narrow tube, which is a huge advantage. That cleanability that you were talking about with, the tube and shell, a plate exchanger is just designed for that high volume throughput, and so you're not going to have that kind of clogging that you get over time from a coil in the same way. And it's going to take up way less space in the facility compared to just series of big giant coils that require a lot of external insulation. A plate exchanger kind of insulates itself, which is really, really efficient. It's the standard in like brewing for a reason because you just aren't going to get better numbers in terms of surface area, efficiency, and flow. Normally, you have to compromise on one or two of those to get the temperature you want, but we can push a lot through it and get a lot of performance out of it. And like I said, small, mounted on the wall, get it up high. It's a delight.
So we're running
Absolutely.
pretty low on time here. I'll feed you guys with some questions. If you want to just answer them at the end here. Do you have any more slides?
Nope.
Okay, cool. Is there a way to determine the quality and quantity of the biomass before you extract the biomass? Are there certain strains and growing methods that lend themselves better to extracting and crystallizing?
For me, highest THCA is better, and we prefer running, there's dry pure biomass that we don't really have to freeze beforehand. But if you're trying to produce live resin, you want to have the nicest terpene profile that you can because that is impacts the value, right? So it depends if you're making isolate or fresh frozen. Fresh frozen, you want a nice terp profile. Isolate, you just want as much THC as possible.
And then with the
I
controlled
would
crash,
also, oh, go
sorry.
ahead.
Well, with the controlled crash method, we can kind of crystallize some pretty low quality biomass as long as it's high in THCA. So a lot of times people will actually use the low quality stuff, crystallize out the THCA, and then just try and actually recover some of the remaining THC from the HDA, and it's really not like a value stream for them. But then they're mixing the THCA back with the like higher quality terpenes, and then you're able to get a lot higher quality overall product without kind of while you're actually utilizing all the lower quality biomass and the fresh frozen biomass.
We've
Yeah,
got
I would
three
say the
seconds.
age. Oh, is it going to cut us off?
I don't know what
No,
happens.
no, I think we can just keep going here. We've got another
Okay,
Oh,
few minutes,
perfect.
so let's try and get to the questions.
okay.
Yeah, I would just say look at the age of the biomass. If your job is to choose which pile of dry trim to purchase for processing, the age of that biomass matters a lot because the older it is, the more degradation you have in the categories that aren't the THCA or aren't the terps. THCA you
Yeah.
can check with the COA, terps you can check with your face. What you really want to know is how waxy is this going to be from this batch to this batch? How much post processing am I going to have? Am I going to have to deal with a lot of like half degraded weird volatiles or, dark red colors? And so check that harvest date and,
Yeah.
ask for that and ask for the potency test elapsed if it is old, because that'll give you a lot of insight into how it's been stored. The lower the D9 content is in the
Yeah.
flour, the better. Some D9 content is going to occur while you're out there growing, especially, depending on if you're growing outdoors somewhere or growing somewhere with a lot of heat. But fundamentally, if you're like over 2% on D9, that indicates to me other issues besides how much THCA yield am I going to get? It's like, do I have to recrystallize it 3 times to get that yield? Because if that's true, I'd rather have a lower potency, more recently harvested and do it once and go home.
Yeah, D9 is definitely the single largest inhibitor of crystallization capacity. So
So
watch out
D9
for
as
that.
opposed to THCA, right?
Yeah,
Whereas
Yes.
THC as opposed to
carboxylate.
THCA, the acid form, which is yeah, what you're crystallizing. D9 is not
And,
crystallized or not.
and FYI, if anybody, we're at the time limit, but we're going to keep going. If anybody needs to jump off, just before you head out, if you want the recording, we can send it to you. So just type recording into the questions, and we're going to keep answering some of these questions. I think this is a really good one. Thanks. We use an MVP 150 for active recovery. Uh, I've thought about going passive, but I don't see how it's feasible with multiple columns running simultaneously. This is from John Davy at Neura Cannabis.
Fun fact about the MVP, you can run passive through it by just not turning it on
Cool. Because
Um,
the reeds
because
basically
it's
just
open.
stay flat.
Yeah.
Yeah.
yeah, so let's go back, or actually we can show it on this slide, but really the way that you're running a column while running passively is you pump your liquid solvent. So you can use what a lot of people use, some systems use is they pressurize their tank with nitrogen and you can force it through the column and into your collection pot. Then you off gas the nitrogen and it goes back. But with the liquid pump, what you're doing is you're pumping the liquid solvent out of your solvent tank and into the high pressure zone, which is the collection pot. And then it's recovering passively through the heat exchanger and collecting at the same time. And so you can have a column running at all times. We like to look at the system as continuous. It's always recovering solvent, it's always running, and the columns are batch, and you're just switching them out one at a time. But really, I think that liquid pump is the differentiator.
Murphy, did you want to touch on that one?
I think, I mean, the liquid pump is a huge value, especially if you have already made the investments in chilling your solvent with enough kilowatts. If you actually can get that -50 solvent in the tank, you are really working against yourself by, pressurizing that with nitrogen and warming it up every other column and then depressurizing that nitrogen to keep recovering. And so the liquid pump is a pretty critical shortcut in that. However, you can also overcome it with the volume of your vessels. And so one thing I always like to recommend is to not create a bunch of dead space that doesn't extract in your columns as well, because a lot of people put a bunch of filters underneath their material. And so then you just have like this, 12 inches or so of space underneath where the material is that gets full of solvent that isn't doing stuff. It isn't extracting that material. Its exposure is very limited. And so you end up having to use more energy to push it in. If you look at your columns from the opposite approach, give yourself way more headspace and keep that material near the bottom so that just naturally the gas is going to be where your material that needs to be extracted is going to be really helpful. Because I find that a lot of people kind of work against themselves in terms of solubility, where they try to put as much material in the column as they can, and then they have to use more solvent than the size of the columns in their system is really designed to accommodate. One thing I used to bring up a lot when we had like that 1300 extractor from ETS versus like the MEP, their bigger one now, is that when the 1300 was designed, we were processing trim. No one had put a harvested flower, that was worth smoking into the extractor before. And so we doubled the potency of that input material when we started running things like, whole buds and even just the increase in THCA over time through this industry. And so if you are finding that it's hard for you to fill your columns and that start and stop is killing you, putting less material in the column so that you can use the amount of solvent that's easy to transfer goes a really long way. If you put 1,000 less grams in your column every run, but we're able to turn that column over twice as many times, you would make more product every day. And financially, that is the right choice. Buy less weed, get more hash, work the same amount or less.
And that's one of the key things with the pump too, is that, and actually we haven't even really talked about this, but we have doubled the actual net production of THCA at some facilities by just getting them to run more solvent over their columns. So whether you reduce the amount of biomass that's in your column or you use the pump to pump more solvent over it, you
Yep.
can prevent leaving THCA behind. So your column changeovers are the same. Often your column time doesn't increase. You're just pumping the solvent faster and recovering it faster, and you can just increase your total THCA output per day or your crude output per day, whatever
And
you
the
say.
prerequisite of that is you have to have the recovery capacity. I think that's mostly the bottleneck, and the reason why people are limiting how much solvent they're using is because the limitation for them is how much they can recover, right? And so,
Yeah,
well, how we approach it is we eliminate that bottleneck, and then we get to the point where how much vapor you can recover is not a constraint. And then that allows you to actually get a lot more out of the biomass, right? You're getting what, between 90-95% of what's in the biomass. And that difference, even if you're getting a 5% difference over what you're getting before, it can result in an enormous increase in profitability. It's not a 5% increase in profitability because that 5% extra goes straight to your bottom line.
Yeah. And really, it's, if you increased the yield of every run you did in 2024 by 1%, you wouldn't have time for this webinar because you'd be on vacation. You know what I mean? Like if you could actually hit your bottom line by a whole number in your average yield, it's enormous. And everyone is throwing away more than whole numbers in their biomass when they don't fully extract it. So, you're going to have a bottleneck somewhere. The key is like, did you pick the bottleneck or did it happen to you?
Right, exactly. You're either in control of it or you're at the effect of it, right? And
Mhm.
this is um, this is actually a really interesting topic, the how to maximize the yields in your extraction process. That's another webinar that we're going to do. We're actually going to launch a video on it first, and then we're going to turn it into a full webinar. So just hit yields into the comments if you want us to invite you to that as well. Um, Moving on to the next question, a lot of people in here I think have either ETS, MEP, MEP Mini, or the bigger MEP. I think MEP 30. We've done a number of projects upgrading the MEP 30s. And Lyndon, can you kind of talk up to us about like what are the throughputs like once you tweak that system out to do the full passive recovery?
yeah. Once you get a plate exchanger on there, so you typically go from about I don't know, one pound a minute up towards, two and a half is pretty achievable pretty quick with some passive recovery upgrades, and then we always shoot for 5 pounds a minute to kind of try to 5x the
And
system.
pounds of solvent or pounds of biomass?
Pounds of solvent, sorry.
And
Just talking about recovery rate, but that is directly proportionate. So to the
so you're
amount of
getting
biomass
about
that we treat.
2x increase, and I guess that would be relative to what your solvent to biomass ratio is too.
Yeah, so between a 3x and a 5x, but assuming your solvent ratio is the same, then you would 5x, you'd be able to 2x to 5x your throughput. But then if you're also running more solvent per column, you can decrease that a little bit. But anyway, yeah, we often what we do to upgrade those systems is we add on a bunch of passive recovery upgrades, and then we add a larger collection vessel, and typically the option of crystallizing at scale to kind of round that out.
Cool.
Yeah.
Uh, John's asking, do you have a kit that you sell that covers all of these upgrades?
Yes. Multiple. So what we typically do is we have a consultation, which is typically an hour or two where we go through the lab, we see what equipment you guys have. We often find the equipment that you already have and we can reuse, and then we have various kits that we can plug in. But the whole idea is to have these modules that can be really easy kind of plugged into an existing lab. But yeah, first and foremost, we look at what you've got, and then we go from there, because everybody's got these graveyards, these scrapyards, and often we can increase people's process significantly with some spare parts, even as we go to get some.
If I could make a recommendation, if you are running an ETS system with those coil inside a coil heat exchangers, um, just swapping that out for a plate exchanger is going to make an incredible difference in the way that your system operates, even if you are still too scared to get rid of the recovery pump or make any, or can't, afford a liquid pump, can't change
Mm.
your chiller. If you can only make one change, I would trade the coil for a plate exchanger, because of the efficiency and because if you are using those coils, you need to thaw and blow them out with an air compressor pretty often. A little bit of ice buildup in those coils will not stop your recovery. It slows it down until the pump gets so hot that it thaws it out backwards and then it goes faster. So if you feel like your recovery goes faster at certain parts of the day or that certain staff are faster at their recovery, you probably have old dirty water in your coils and you need to thaw them out and blow them out
It's a
because
ghost.
it just clogs up real easy and it clogs up with particulate. And if you ever accidentally aspirate any oil or anything, if you're using molecular sieve beads, that dust can go into the coils. Coils are not the best solution for the type of heat exchanger we need. And that plate exchanger will eliminate all of those problems. It'll give you so much extra free time to consider the rest of your upgrades.
Yeah, and as far as kits, there's also a kit with the plate exchanger and the liquid pump, and that's a specialized liquid pump that's specifically designed for really cold liquid butane down to -60. And so yeah, it's specifically designed for the application as well.
Yeah, just to so that people don't get misled by the liquid pump, we're using one that's rated for -60, and it's been properly built and redesigned with special diaphragms to be able to handle the low temperatures. Not any diaphragm pump will work. You don't want to get one that's not rated
Yeah, and material
below this.
compatibility is another
Yeah.
important thing to consider, right? Like if you get something, most diaphragm pumps will have a diaphragm that's not compatible with butane. Will freezing cured biomass help with that degradation over time, hence the extracted color once extracted? We keep our
Yeah.
cured biomass room temp after harvest, and we have had issues outside our extraction temps getting sellable extract based on the color.
Yeah, I would say consistency matters more than the actual temperature. What you don't want are swings. So even if you do freeze it, I would only freeze it if you can keep it frozen until the second it's going to go into the column, for example. So you don't want to store it frozen and then take it out and have it sit for a week before it gets, processed. And you don't want to go into a room temperature room that gets hotter and colder at night. Those temperature fluctuations are going to be worse over time than anything because they're so difficult for you to repeat. And so by the time you find out that it's a problem in your extraction process, time has passed and it's very hard for you to respond to it.
Yeah, there's a lot of techniques for how to properly freeze biomass. We see people make these, pillow shaped packages that get good airflow within the walk-in freezers. That works really effectively. But yeah, if you do it wrong and you bring a super sack into a walk-in freezer, you could thaw everything else around you and destroy your
Yeah.
Hundred%.
biomass.
Yeah.
Just because the heat
Hmm.
in that
Or
biomass.
or if you're keeping it in chest freezers that have an auto defrost, so they're just thawing out, every 40 hours or whatever, and literally a heater turns on inside. So like you don't want to just, I would also say you do not want to go colder than your extraction temperature. So if you have a -80 freezer and your extraction is actually happening at -10, you are thawing out your material when you put it in the column and expose it to what is now fundamentally warm solvent because you've got a 70-degree gap between your process and the material. So if anything, you want your solvent to be the coldest, and so a regular chest freezer is more than cold enough for storage, in my opinion, but your ability to maintain that is really key because cheap chest freezers are either full up with ice and not getting as cold as they say they do because they're full of frost, or you've got something that's manually defrosting and you've got to consider that for that lifespan. And a walk-in, same issue. If you're not maintaining that compressor and you're not keeping a good eye on when things are going in and out. For example, don't bring in your ethanol that you winterize with into the same freezer where you have your fresh frozen stored because you will get that thawing effect. It's got to average whatever else is in the freezer with it. And so holding temperature is really key. If you can keep the temperature from ever going up again, that's the right temperature to store it at.
Cool, awesome. What is the average solvent to biomass ratio in a 10-pound column? Also, average solvent to THCA ratio in terms of crystallizing. That's a good question. Matt
Yeah,
Nenner.
Yeah, so off the top of my head, we typically see, it depends a little bit on your solvent temperature for primary extraction, but we see like 3-to-1 to 5-to-1 to solvent to biomass. So, in a 10-pound column, if you can actually get 10 pounds in there, then that would be 50 pounds of solvent that you're sending through it on kind of the higher end. But what we do is we put a sight glass in line after our columns and we run them until we don't see any more, don't get any more crude out of it. That is really the most effective way to determine that you're using enough solvent. And then when we're doing our crystallizations, it's often in the 1-to-1 range. When you're actually going to be running a crush, it's around 1-to-1 butane to THCA. I assume that's what they mean. If you mean extraction capacity, then it would be about 50-to-1 because you have 10% THCA to your biomass weight and you're using 5-to-1 solvent to biomass. So you get 50 pounds for 1 pound of THCA.
I think surface area is an important component of this as well because you can just keep running more solvent over it to overcome a column that's too tightly packed to get good surface exposure. But how much you break up your material, there's a too much and a too little that can exist. And there's a lot of factors that would influence this. Personally, breaking up fresh frozen is like not a fun task. And so I opt for putting less fresh frozen in a column so that I have a greater ratio of solvent to biomass inherently, so that I don't have to spend more hours in the walk-in freezer with like a hammer or whatever you guys are all doing out there. And so, you can either invest in good grinding and shredding so that you can get a nice light shred that isn't doing too much damage to the material, or you go back to calculating what's the minimum amount that I can put in a column and get a good level of efficiency out of. And so maybe I put 1,000 grams less per sock, but I'm getting that 96, 97, 98% efficiency versus doing an extra 1,000 grams per sock but only getting a 90% efficiency on what I'm able to extract from it. So if you find that you're having to do a tremendous amount of extra solvent, it may be that you just need less material in the column. The column is fixed. It's kind of the only part that's fixed. You can only fit what it can fit. And so, being able to modify the parts of the process you can control is going to be really helpful there. Overfilling a column does get more grams processed per day from the raw material side, but does not necessarily mean more grams produced of your final product, which is kind of a business management problem more than anything. If you tell your extractors that their job is to process this many pounds of biomass, you are wrong, because your business does not run on how much biomass you processed. It runs on how much product you made. Their goal is, I need to make this much product per day. And you have to shift your focus to that. And so that solubility should always be based on how much final product is there and how many compromises I'm willing to make to get it, how much post processing I'm going to have to do. If I've got some of that old material that's not as good, for example, I'll take a 92% efficiency to not have to recrystallize it 3 times. But those are decisions you want to make and not reactions you want to have, in response to something happening.
Oh, you're on mute.
Question from Parker from Pantheon. What if you're using liquid bulk supply to supply the nitrogen? Is it still going to warm the solvent? There's probably a liquid nitrogen tank, so cryogenic nitrogen.
Yeah, the decompression will probably be pretty chilly. I don't know anyone doing it, from that liquid nitrogen source. But I would say the way to find out would be to measure your temperature. If you've got a good liquid nitrogen delivery system, you should have some thermocouple, points in that process that you're monitoring. And again, I would just consider the idea that the extraction temperature of your process is based on the extraction temperature of that solvent. So you don't want to bring in anything warmer necessarily.
Yeah,
But
from my
probably
perspective,
if, oh, go ahead.
I was just gonna say, for me, it's the cost of the nitrogen is the main thing, right? I really think that avoiding that is.
Yeah, so Lyndon, why don't you tell us then, like, how we're recycling nitrogen through the system, and repurposing the recovery pump that still stays part of your extraction process after you upgrade to a passive system.
Yeah, I wish I had a quick diagram for this, but essentially what we do is instead of chasing our columns with nitrogen, we have nitrogen in the system, but it starts in the solvent tank, and then we use a recovery pump to push it into the top of the column to chase our butane. So we push it in, and then it ends up going all the way back to the solvent tank, and then we pump it out and we put it back through the material column. And that way, every time you decrease the pressure in the solvent tank, the recovery speeds up. You're dropping the pressure and you're speeding up how fast the butane goes back. And we're using that nitrogen to clear all of the butane out of the column so that you're not leaving any behind and having extra solvent loss.
Awesome. This is actually a multi-point question here from Tim. On a passive system, extracting 4 terp retention, so he's not wanting to make distillate, where do you draw the line on N2 pushing? When to determine when you are getting diminishing returns on time, money saving with extra butane? In that same vein, what is the ideal process to effectively remove the max amount of butane from a sock? That's a great question, actually, that we talk a lot about. At what rate, pounds of butane retained versus pounds of material packed, do you consider efficient purging?
Most often, so I kind of work backwards a little bit on this one, but most often we see around 200 to 400 grams of butane lost per column. And the way that you mitigate that is, well, we call it juicing, but essentially what we did is we send some nitrogen to the column. We let the butane kind of leave the plant a little bit. We leave it alone for a second and it kind of pools. And then we push again with nitrogen. We do that 2 or 3 times. And the longer you do that, the more and more butane you can get out of there, but you'll never get it all. The way that we get it all is, you can do stuff like heat your columns and things, but we have found that that doesn't ever make sense from a time perspective to heat your columns to get all that butane back, unfortunately. And so really I view, with columns and that style of extracting is a cost of doing business, really.
I'm gonna say this is the perfect opportunity to stop overfilling your columns as well. So one of the most common reasons that you would have a lot of extra solvent in your column at the end of a run is because of your inability to recover quickly and to recover all of it. So anytime, like when you think about a recovery pump, it's a push pull, and so every time it pulls, things are moving, and then when it stops pulling, things move back just slightly. And so you end up with this ebb and flow at the bottom of your column going towards wherever it needs to go. And that's not good. This system is based on pressure differential, and you want that to be linear. And so anytime you have a push pull, it's breathing against your system. And so if you see the breathing that sort of happens in the pressure gauge on your collection vessel, if that's happening at your material columns, that's bad. That's working backwards against you with every movement of that pump. But you can also have that back pressure in between pushing with nitrogen. So if you push with nitrogen to build pressure, and then you let the pressure build up over in the collection vessel so that it becomes higher, you can push and pull with nitrogen and move it back. And so anything you could do to quickly drain the columns, the faster you get them drained, the less likely you're going to have that little bit of extra at the bottom that's going to work against you. Another thing that's also going to work against you, like I mentioned before, is a bunch of heavy filters underneath the material that can get clogged up with ice when it's nice and cold and running, and clogged up with fine particulate. So then you have solvent underneath of those filters that isn't getting the same brute force as the material on top. And so, if you've always got that little bit of liquid sitting in the bottom, you likely need to either use less material in that column overall, or less of that filtration and spread that filtration surface area out somewhere else. I prefer to filter in another column outside of the one that the material is in, so that way the filter isn't holding the material on top of itself, literally touching, and trying to do particulate filtration at the same time, because changing out filters at the bottom of material columns sucks. Talk about turnover. I mean, I'll put the cap on 1,000 times before I want to take off those bottom filters and reassemble that bottom stack. And so, the way that flow works really has to match that batch size and that solvent recovery speed. So if I run a lot of fresh frozen. I want that fresh frozen to still be frozen when it comes out of the column, and dry. It's dangerous to be pulling it out. It's sticky droplets all over your floor when you are moving it from the column to wherever you let them degas. It's space, literal square footage in the booth that you have to give up when you let it degas for longer in the booth. And so all of those things work against you, where potentially just less material per column, so it's not so tightly packed, will drain faster, extract faster,
Mm.
yield more. And so it feels counterintuitive, but if you start with just 500 to 1,000 grams less per sock, if that saves you 10 minutes, you can run that 1,000 grams again later and get your yield right back. And it will help a lot, because a lot of times that extra solvent trapping is actually like a squeegee effect. And with fresh frozen, you don't want that, because if you're just looking for liquid flowing as your indicator that more solvent is going, that is unacceptable with fresh frozen. You can just juice the water out, and water and liquid butane are the same color in a sight glass. So that is not a helpful perspective.
So it sounds like if you can reduce the amount of biomass per sock, maybe adding additional columns gets you that extra
Hmm.
biomass that you actually want to
Easily.
get in there, right? And then increasing the solvent recovery allows you to flow more relative to the biomass as well, or based on proportional to kind of how much you're actually aiming to extract. I think that's the other second part of the question here is like when you have diminishing returns, where you're not saving time or money anymore, by adding more butane, flowing over the biomass.
Yeah, we look through a sight glass to try and see when the color drops off, and that's really what you're looking for is keratin. And typically that it seems as if that drops off at the same time, so you stop seeing yellow when you stop pulling THK. But also what we'll do is we will send some to the collection pot. Inside of our collection pots, it'll hit the wall. And so you can run a little bit of solvent and you can watch and you can see if it's still leaving behind resin. And that can be effective measurement as well.
I would also recommend use potency testing to analyze your methods. So,
Yeah.
imagine you've got a system with 3 or 4 material columns. Put the same material and the same weight in each one and run a different amount of solvent over each one. Then pop those columns open and pull a sample out of that sock. And I recommend pull a sample from the top, the middle, and the bottom. The bottom you can see. Our socks are stained to show us where we are being inefficient, usually.
Right.
And so
Yeah,
you'll
feel
be
better.
able to identify where that is. If it's always yellow on the bottom third of your sock, the bottom quarter of your sock, you're probably in the normal range. If it's over half or more, you're wasting time for sure. But also, your potency should be even throughout. So if you've got residual potency in your biomass after extraction, it'll be higher at the bottom and less the closer you get to the top of that sock, theoretically. And if things are going wrong, you'll be able to figure out when and where it happened. If it's all happening at the bottom, you're extracting things off the top and then not draining quickly enough. But if it's pretty densely packed with residual cannabinoids all the way to the top of the sock, a lot of things aren't going well. And you probably do need just genuinely more solvent versus biomass, or less biomass per column. The idea of refilling and continually running more and more solvent through one column doesn't work for a lot of systems because their tanks aren't big. I have these 300-pound tanks. Lyndon has big, giant tanks. We're very spoiled. But if you're out there with a 100-pound tank, a 50-pound column, you can't do that because you can't get the other 50 pounds out of that tank as efficiently as you get the first. So,
Great point.
um, so being able to modify the parts you can control for what you have is really valuable there. And like you said, if I have to cut 500 grams off of 3 columns, but I add a fourth that 1500 grams can go into now, I haven't lost any actual efficiency in terms of total biomass per day, and I'll gain in every other category that I'm looking to solve for. So while it may be a greater solvent to biomass ratio, it could also just be a physical problem of make sure your socks are smaller than the diameter so that they slide in and out easily, and make sure they're not overpacked, and make sure you're not grinding everything into keef before you load it, and make sure it's not clogged with humidity before you load it. Take charge of the few easy things. Low hanging fruit, I think, is what Lyndon called it. But those are sometimes very fast. And you can see that through potency testing. And that's also a really good way to measure your staff to know who's the best at their job, because whether you go for that third nitrogen push or not might depend on whether you're hungry in like a legit, large
Yeah.
scale processing facility. And no one's going to say that to you. That's not going to show up on the diagrams, but it is real. Some staff members have a sticky mess underneath their socks and some staff members don't. And so you can trace that back through potency testing by just pulling samples out of the sock.
Maybe test their blood sugar levels as well. No, just
Just
joking.
provide snacks. Yeah,
Panel.
just provide snacks. Trade your cell phone for a granola bar.
Yeah, exactly. Granola bars are key in the lab for sure. Um, but yeah, I think the other thing too is if you're doing the testing and you're below 95, you're extracting less than 95% of what's in the biomass, there's room for improvement. Now, I think one of the things that Murphy mentioned that's really important is like what to do in that situation depends on where you are now, right? Like if you don't have enough solvent in your solvent tank, that's going to need to get addressed in one way or another. Either you're going to be limited by something, and so that's kind of how we will approach it with you. We'll actually just consult and understand where you're at right now and advise, like, based on your budget, based on your goals, what's the best actual next step to address these constraints, because every single system or every position that you're in is going to have a different constraint or potential constraint. But step one is just getting the data. Get that data and then bring it to us. We can help you understand exactly how you can improve that number. I think that's pretty much it for questions. Just gonna wrap it up. Thank you guys so much. Thanks, Murphy and Lyndon. You guys are amazing. Wealth of knowledge. I know there's been so much appreciation in all the questions as well from the community. So people really, really appreciate the support. We try and be as, kind of an education first, offering. We're all about, you know, giving back to the community as much knowledge as we can and supporting. We also have a crystallization community that both Lyndon, me, and Murphy are all pretty active in. And honestly, people are messaging in there like there's like 20 messages a day where people are helping and supporting each other. So this is the kind of thing that we really like to be a part of and provide as a value proposition to the community. So you can type community before you head out, and if you want to join that, it's always a great way to kind of get your questions answered as well. And if there's any questions that we haven't addressed, our team's going to be reaching out to you guys. We have your emails, so make sure you check for your emails. I think it's going to be Karsten who's going to be in your inbox if you had a question that we didn't get around to, and we'll make sure that we get all those answered for you guys and get you guys supported. So thanks for coming, and yeah, have a great rest of your day.
Okay, see ya.
Thanks for having me.